This is Lab 3, Working with Black Holes by me, Alex Arredondo. So in this lab, we'll be testing our knowledge of Newton's second law. In code 1, we'll be predicting the motion of a star orbiting around a black hole. Then in code 2, we'll be using position and velocity update equations to find the rocket's trajectory along the path of a black hole. And then I'll be answering some what if and some what does it mean questions relating to how to orbit a black hole and the difference between the net force and dp dt. All right, so fundamental principles in this lab are Newton's second law, the momentum principle, and rearranging Newton's second law to get the update formulas. All right, so in code 1, we're asked to find and predict the motion of a star around a black hole. We have a known mass of the star, but in order to predict the motion properly, we need to know the mass of the black hole. So we are solving for the mass of the black hole. Our system is a star, and our surrounding is the black hole. Here's a preview of our results. As you'll see, the forces get larger as they get closer to the black hole because they're getting more attracted to the mass of the black hole. And the mass of the black hole is actually found to be 1.32 E34 kilograms. Crazy big. Our initial conditions are given to us in the lab opening. They say it'll take us 1 day, so in order to convert that to SI units, we just multiply 86,400 seconds. The mass of the star, which is 2.0 E330. And then our star initial conditions. This is found by putting in your GT email address, and it will randomize the initial position as well as the initial and final velocities. All right, so in our code, we are using P equals mv, assuming that the star is traveling less than the speed of light. Then we are solving for delta V and delta P. This is just the final minus the initial of the respective components. Next, we are going to say that F net is equal to dp dt. This is based upon Newton's second law. Now we're going to get into the nitty-gritty. So p hat is equal to p divided by the magnitude of p. This finds the direction of the momentum. Now we need to find d magnitude p divided by dt. This can be found by doing the magnitude of the final momentum minus the magnitude of the initial momentum divided by the change in time. So this will find the change of momentum at different times, or the change of momentum at the change of different times. So now we need to find dp parallel divided by dt. And this is just equal to delta p hat, or yeah, delta p magnitude divided by delta t times the p hat. So this just gives us all that in perspective of what our dp dt parallel is. And so, like we said above, we know that the F net is equal to dp dt, so we can assume that F net parallel is equal to dp dt parallel. And that's because we have no other forces in this direction other than just the gravitational force. And then we can rearrange this equation to solve for F net perpendicular, because we know that F net is equal to the perpendicular and the parallel components added together. And speaking about rearranging equations, we can rearrange the gravitational equation to solve for the second mass, and that looks like what we have on the left. Now getting into code 2, this question is asking us to find the interactions of multiple forces on a spaceship whose thrusters are not working with initial velocity that we are changing. So our system is the rocket, and our surroundings are the planet and the black hole. So here is the preview of the results. Very cool. And then our initial conditions, we have the mass of the black hole that we averaged from the last one that we put into Excel, and then found the average of all of those data points, and we found it to be 1.32 E34. The mass of the planet and the mass of the ship, which are both given in our sample code, and then our initial velocity, which is just guessed and checked to get the closest position to the black hole, the black hole's event horizon. All right, so now let's break into it. Code 2, we're basically repeating the same task over and over again, where we're just finding the distance between 2 points, then we are finding the magnitude of that distance, and then we are finding the direction in which the force is being applied to, and then we're plugging into the gravitational formula. Very, very cool. Now, however, we have to see what that all means. So if we have if we have two forces, what does that mean? Oh no, we have to find the net force. So we have to sum the forces together. Very, very nice. Now, and then on line 103, we can actually save ourselves a little bit of work because we know that F planet on ship is equal to the negative F ship on planet. This is because we know reciprocity laws. And then on line 105, we're just doing the same thing, just summing up those forces. All right, now we get into the update formulas. So we use both the update formulas on position and velocity. And since we know that the force is constant, we know that the average is equal to the final velocity. All right, now we're getting into what does everything mean? What did I just talk about? So when we're talking about F net parallel and perpendicular and dp dt parallel and perpendicular, there's not really a difference. However, when we're trying to calculate things, there does come some differences. So we were able to calculate dp dt with a known initial mass and velocity. However, when we want to use F net, we need to know the mass of the second object. This is why our methods are similar in part 1 and part 2, but not entirely the same. Uh, this could also be a potential source of error, if any, because we are assuming that F net is equal to dp dt. So now, getting back to the second code, what would happen if we wanted to orbit around the black hole? So we would just need to have a greater y initial velocity compared to our x velocity, and this will give us the ability to orbit around the black hole if we want to observe it any longer. All right, that is it. Thank you for watching, and have a great day.